management problem is all about is that, assuming as a manufacturer or as the owner of an organization, you have different assignments and you are thinking of, instead of calling this education, can we call it activities? Activities. Now, you have 4 activities and you have 4 machines. One of the assumptions is that the number of machines must be equal to the number of activities. What you are looking at is if you give activity A to machine 1, a minute. Activity B to machine 1, 4 minutes. Activity C to machine 1, 6 minutes. Activity D to machine 1, 3 minutes. In that order. The question is, which activity should you give to which machine for the purpose of having minimum processing time? That's just what it's about. Which activity should you give to which machine, or which activity should you give to which individual for the purpose of having minimum working time? It can be another way. If you give activity A to machine 1, the reward is 10 naira, 20 naira, 30 naira. It becomes a maximization problem to say which activity should I give to machine 1 to get the maximum reward method. So it's just a way of allocating activities to individuals or machines for the purpose of minimizing cost or maximizing reward. The illustration above is about maximizing reward. This is the original matrix. To solve a minimization problem, the very first step is develop a row reduction matrix. A row reduction matrix. That's the first step. This is how to solve minimization problem. When we get to maximization, I will tell you. A row reduction matrix means you have A, B, C, and D. Here you have 1, 2, 3, and 4. To get a row reduction matrix, the rule says identify the least element in each row and subtract it from all elements including itself. 1 is the least here. 1 minus 1, 0. 4 minus 1, 3. 6 minus 1, 5. 3 minus 1, 2. We are doing a row reduction matrix. Here, the least is 7. 9 minus 7, 2. 7 minus 7, 0. 10 minus 7, 3. 9 minus 7, 2. Very, very easy. Here, least is 4. 4 minus 4, 0. 5 minus 4, 1. 11 minus 4, 7. 7 minus 4, 3. Here, the list is 5. 8 minus 5, 3. 7 minus 5, 2. 8 minus 5, 3. 5 minus 5, 0. Then the next is that you do a column reduction matrix. Column reduction matrix. You do a column reduction matrix. In the column reduction matrix, you plot again A, B, C, and D. Then you have 1, 2, 3, and 4 in machines. So, in the column reduction matrix, in each of the columns, you identify the least value. Here it is 0, that is the least value. So if you take it away from one, you are still going to get the value 0, 2, 0, 3. The next column, 0 is the least also. It will retain. Oh, sorry. This is supposed to be A, B, C, and D. So the next one, 0 is the least. You see, you have 3, 0, 1, and 2. The next one, you have 3 as the least. So you can have 5 minus 3, 2. 3 minus 3, 0. 7 minus 3, 4. 3 minus 3, 0. The next one, the least is 0, so it will remain constant. 2, 2, 3, and 0. Now, since we have done row and column reduction matrix, the last step is the one you must be careful about. You draw an imaginary line to cover all zeros and make sure you use the minimum number of lines possible. It means you must cover where you can cover highest number of zeros first. If you cover this way, you will cover 2, have you?
Yes, sir.
If you cover this way, you will cover 1. If you cover this way, you cover 2. If you cover this way, you cover 1. Listen to the rule. You must cover all zeros with imaginary lines. And make sure you cover with, you first cover where you can cover highest number of zeros. That's 1. 2, the number of lines must be equal to number of activities. If it's not, you move forward and do another surgical operation. So, if you cover here, you cover 2. If you cover here, you cover 2. If you cover here, you cover 2. So that means, anyhow, 2 is the highest we have been able to determine. So cover anyhow, where you can cover 2. I want to cover 2 here. After that, I want to cover where I can cover 2 again. I can cover 2 here. I want to cover where I can cover 2 again. Abi? I can cover 2 here. So I've covered using 3 lines. I've covered using 3 lines. Now, if you look at this, we have gotten 3 lines and we have 4 assignments. It means the solution is not optimal. At this point, if the solution is not optimal, we'll go to a modified matrix. Modified matrix. In the modified matrix, we have A, B, C, and D. Here we have M1, M2, M3, and M4. In the modified matrix, you identify the rule to do the modified matrix is you identify the least uncovered element. What is the least uncovered element here? 1. Abi? To identify the least uncovered element, you take it away from itself and all other uncovered elements, but add it to all elements covered by 2 lines. Identify the least uncovered element. Take it away from itself and all other uncovered elements, but add it to all elements covered by 0. This is the way to do it. The way to do it is to first of all write out all elements that are covered, because we won't do anything to them. The elements that are covered are 0, 2, 0, and 3. Here you have 0, 0, 2. Here you have 2, 0, 0. However, out of all these, anyone that is covered by 2 lines, you must add 1 to it, because 1 is only the least uncovered element. So 1. That means these 2 will become 3. And these 3 will become 4. All other elements, you take away 1 from them. 3 minus 1, 2. 2 minus 1, 1. 1. 1 minus 1 itself, 0. 4 minus 1, 3. 3 minus 1, 2. That's it. Now you can cover. So when you want to cover here, you cover with imaginary lines, covering with where you can cover higher number of tables. 2, 2, 2, 2. That's the way it is. We can cover anyhow. Let's assume we want to cover these 2. I mean, what do we have 2 again? You can cover 2 anyhow. You can cover these 2 if you like. You can cover these 2 if you like. You are left with what? 1. You can cover 1 like this if you like. How many lines have we used to cover now? 1, 2, 3, 4. Because the number of lines are now equal to numbers of allocation, then it means the number of lines now equal to the number of assignments you can allocate. To machine 1, to machine 2, to machine 3, to machine 4. To machine 1, wherever you have 0, you can allocate A. To machine 2, you can allocate B or C. B or C. To machine 3, you can allocate A or B. To machine 4, you can allocate C or D. Now, since you have options that they need for you to scientifically allocate from where you have only one option only. I eliminate that option wherever it exists. Machine 1 has only A, so A must go for it. Machine 2 has no, and you cross A wherever you have it. Who is having only one machine again? Machine 3 is left with B. You cross B wherever you have it again. Machine 2 is having only C. You give C. You cross C wherever you have it again. Machine 4 will be having D. So you have A, C, D. And what's the time? Allocated. Allocated machine 1, if you give A, is 1 minute. Machine 2, if you give C, it is 10 minutes. Machine 3, if you give B, it is 5 minutes. Machine 4, if you give G, it is 5 minutes. Without conflict, this is 21 minutes. I want to challenge you. Do other allocations and see whether you get anything less than 21. This is the least you can get when you are doing a minimization problem. You allocate zeros to each of the machines, and when you do that, you identify where there are clashes. Start from the one that is having only one option, eliminate it from wherever it is appearing. With that, you are through with the minimization problem. Thank you.